Okay, hello everyone. I am Khiem. I am here with Zach, Suhas, and Levi, and we're presenting to you a combined peer-to-peer tutorial on how to make your code more accessible. Just as an outline of what we're going to be talking about today, I'll be giving a brief introduction to the subject. Levi is going to be giving you some ways to make your code better using good coding practices. And then we're going to really dive into Google Colab as an example of how to really make your code more accessible to non-coders. And in this section, we're going to have a few demonstrations, and we hope that you can interact with as well. And we're going to provide a link to our Google Drive folder that contains these slides, as well as those demo files for Google Colab, and hopefully you can be able to run those on your computer as we show them. And then feel free to type questions in the chat and we can answer them there, or we may elaborate more as we go along in the presentation. Right. So first off, why publish your code at all? I mean, the real big reason to publish your code is it allows for reproducibility of your work and replicate and be able to replicate it. And it's actually a requirement for most journals. So when you publish your work, you're likely asked to publish your code alongside it. And it's going to help maintain a publicly available scientific record of your work, so people can see like what you did, when you do it, and even see your progress over time. And it can help others with their research. They can use your code to analyze their own data sets or even improve their own code as well. And having it in a public form can lead to improvements of your own code and lead to better iterations of your work. And GitHub is one popular option to publish your code. And there is a previous peer-to-peer tutorial on this that we encourage you to look at as well. First off, what I want to talk about is a little bit about the reproducibility crisis. And so in this survey of 1,500 scientists, they asked them if they think there is a reproducibility crisis in their field. And the majority of them agreed that yes, there is. And as some of this might be attributed to maybe biological experiments and reproducibility there, but some of it can also be attributed to reproducibility of analyses. And due to the cross-disciplinary nature of many research fields nowadays, and the availability of large data sets, many analyses require some sort of custom code. And these codes are not well documented and many times aren't published because maybe people think it's not publish worthy or it's just too minor to even put out there. But all of this really contributes to the lack of reproducibility. And the problems with codes that are actually published is that there is a lack of standardization. It can be hard to use because of this lack of annotation or documentation. People who are not familiar with that particular programming language may have difficulty using it, and as well as there being no clear dependencies or outdated dependencies if you're not updating your published code over time as well. And overall, what we think is that the easier your code is to use, the more impact it's going to have, the more citations your work will have as well. And so here we have a example from Levi that he graciously provided us, which he posted some code into GitHub many years ago. And as you can see, there's no documentation, there's no description of what the code is, what it's used for. And this is kind of far too common on GitHub, where you might see code with no information and nobody can use it. So is it really available if no one else can implement your code? So this is something that you want to think about when you're going to be publishing code. And so this kind of brings us to around to the point of accessibility. So what we think of code accessibility is how long would it take someone to run or implement your code? And this can vary depending on the experience level of the user, whether they have a background in the field or even know the programming language that you're coding in. But overall, we kind of divided this into two groups where you have coders or non-coders. So when we think about coders, these people may want more descriptive methodology on your scripts. They probably want it organized into functions or modules where they can pick and choose pieces of code to use for their own analyses. And oftentimes they're able to troubleshoot any issues because they're familiar with problems with the programming language or specific tasks that they need to do. However, with non-coders, they really want an easy input and output. They don't really want to have to download or install software dependency because that may be very difficult for them. And if they can run it via a website, that's like the best case scenario, so they don't have to install anything at all. And most of the time, they're probably unable to troubleshoot issues because of unfamiliarity with the task or programming as a whole. And so next, Levi is going to talk to you more about how to improve your code for non-coders.
All right, I've requested control, Zach. I still can't change the slide. Oh, there it goes. Great. All right, so I'm going to talk to you guys about 4 ways you can improve your code that hopefully aren't too much work. I really tried to pick 4 things that I thought were the most impactful with the least amount of work. And they assume a couple things, which I'm just going to mention quickly. They assume that you've already organized your code into functions, so that it's not just one big long file. And that's pretty much the main assumption. You've organized things into functions, which is like a basic coding practice that we're taught early on. But these 4 things that you can do to really like help other programmers use your code in order are license. This is the most important. Doc strings, which is a form of documentation that's pretty easy to use, a linter, and an auto formatter. So let me take you through these one by one. So the first thing is a license. A license is a document, a short document usually, that you can add to your code repository or at the start of each file. And it allows somebody to use your code inside of their own projects. Without this document there, without some form of a license, they run into a lot of copyright problems if they try to use your code, because you as the code writer by default hold the copyright. So there are a lot of licenses out there. Every company has their own, and open source people also have their own. So if you want to open source your code, the good news is there are several open source licenses that you can use. There's 3 main families. There's the GPL family, and then there's the MIT and BSD family, and the Apache family. And basically GPL is if you want your code to stay open source. So if you want to open source your code and you don't want a company to take it and use it and hide it, that they have it. That's what GPL is for. Then there's MIT and BSD, which basically say you can use the code for any purpose and you can't sue me. And then there's the Apache license, which has a bunch of other legalese about patents. In my personal experience, most academics use MIT and BSD because they are not necessarily worried about patents, and they're not necessarily worried about other companies using their code for commercial purposes. In fact, sometimes that's the point. But I'm going to link this website here, choosealicense.com, which does not give legal advice, but clearly explains in layman's terms what each license has or doesn't have. So for instance, I have a screenshot here from choosealicense.com for the MIT license. And you see on the left, it says what you can do, what the conditions are, and what the limitations are. Basically for MIT, they cannot hold you liable, they cannot sue you, and they can't claim you gave them a warranty, which would mean that you have to support the software. But they're free to use it for pretty much anything they want, as long as they include the license and the copyright notice. So at least you'll be credited. All right, so the next thing to talk about is doc strings. And these are a little specific to Python, but as you'll see, they are not necessarily, you can do the same kind of thing in any other language, really. What it is basically putting documentation in line with each function in your code. So this goes above a level beyond just putting comments in your code that would line by line explain what each line is doing. Instead, this explains at a high level what a function's inputs are and outputs are. And that function could have tens of thousands of lines of code in it. I hope it doesn't, but if it does, that's okay. And all somebody would need to know is what to put in and what they would get out. On the right, we have the docstring for the numpy ones function. This is a function that returns an array of ones, which seems pretty simple. But as you can see, the docstring for it, which is actually the documentation for this function, is quite lengthy and very detailed. The formatting is also specific. PEP 257 is a document that lists the full specification for Python docstrings. I don't usually follow PEP 257 to the letter. I just write something that looks vaguely like a docstring so that if somebody comes into my code and is looking for something useful, they can read something like this. But there's an advantage to following PEP 257, which I'll explain in a second. So you basically would type one of these at the start of each function of your code to say what it takes in, what it takes out. I cut it off for the numpy ones function, but there was actually examples for how to use it down below the last line there, which is very nice. But yeah. Now here's if you follow PEP 257, if you follow the standard for your docstrings, then it's actually possible to run your code through automatic documentation generators, which can make some really professional looking documentation that you could distribute with your code or put on the website for that paper. And so here's the example again of the numpy ones function, what that docstring actually generates into. Now I'm sure Numpy is using a custom theme with their docstring generator, but that's, yeah, I mean, the default themes are fine. Most people will be impressed that you even have a docstring as a graduate student. And the library to do that is called PyDoc. It's built into the standard Python library, so you don't need to install or do anything special. You just need to follow the PyDoc instructions. Now the next good practice, and these next two are to help you make code that kind of looks professional. So the first thing you do is you can run a linter. And a linter is a program that usually you would run over and over during development, maybe every time you save the file. And it tells you little issues that are in your code that you could fix to help it be more readable. These are usually things like, this wouldn't point out something that's incorrect with your code. It would just point out something that could be written better, if you want to think about it this way. And on the right, I show an example of this. We have at the top some reasonable looking code. We're going to run it through a linter called pylint, and pylint will print out a list of things that it thinks could be fixed. For instance, on line 3, character 0, it says unnecessary semicolon, the first error there. And if we go up to a box above, we see that it says import string with a semicolon. In Python, semicolons are not needed at the ends of lines. It doesn't make sense, but sometimes we accidentally type them, especially if we come from programming C or C++ that day. So it caught that and it'll tell you, and you can remove that. The other thing it can do is it can tell you if you're missing your docstrings. So it says right away that this module, this whole file is missing a docstring. A file can be considered a form of a function. So that's a good idea to have docstrings there. And then it also has noticed that there's constants at the top of the file, these variables that are global constants, which are fine. But in Python, we normally name these in all uppercase. And that tells people using our code that these are constants and they don't need to worry about them changing and so on and so forth. So the linter has caught that and is letting you know that you should properly capitalize it. And if you take all these things as a whole, they don't make a large difference to your code, but they make it much easier for somebody coming in later who might not be 100% familiar with what you're doing and definitely isn't familiar with your code, and they will more easily be able to pick up in the middle and work on things because things like constants are capitalized, so they don't have to go searching through the file to figure it out. Anyway, so if I've convinced you to use a linter, I'll just tell you now that there's two main ones. There's pylint for Python and flake8. I'm not super familiar with the differences between the two, but those are the two most popular ones by far. And if you Google Python linter, you will get a ton of hits with a ton of different results. So these are the two that I recommend. They seem to be the most popular. The next thing you can do is you can run an auto formatter. An auto formatter, unlike the linter, which recommends things that you could change, it actually rearranges your file and actually fixes things for you. So it's a kind of a more drastic step. And you should you want to trust your auto formatter to do a good job, because sometimes you can't check all of its work. So an auto formatter will rearrange the spaces, the lines, the commas, everything in your file to make it more readable. And it can also help with things like if you have written a really long line, let's say you wrote a 400 character line in your Python file, it might help rearrange that so that it's only maybe 80 or 100 characters long per line, but still maintain ease of readability for the person coming on later. And so there's another standard for this called PEP 8. So Python has its PEP standards. We talked about PEP 257 earlier, and now we're talking about PEP 8. But PEP 8 is a standard that says how code in Python should be formatted. Not that there's valid Python that doesn't conform to PEP 8, but PEP 8 is supposed to maintain the readability. And Auto PEP 8 is a program that will do that. And then YAMPF is a program that will format your code to PEP 8, but in the best way. And this is what Google actually uses. So on the right, I have an example of auto formatting a piece of code with YAMPF. So we have this code. It's got extra new lines we can see. It's got weird spaces everywhere that don't need to be there. From class to the last defined, there's almost no new lines, which makes it very hard to read. And we push it through YAMPF, and we will get a very nicely formatted piece of code that's much easier to understand. So usually if I'm doing a project, I will run a linter while I'm writing my code so that all these linting issues don't show up. And then when you're done, you can put it through an auto formatter, make sure it still works, but hope that you get some more readable code. And these things will help you a lot, because if you did all these things by hand, they could take a long time to get your code all formatted in a nice way. But if you use these tools, it'll help you a lot, and it will help the people who come after you. All right, so those were the 4 things I felt like I should mention to everyone that are quick and easy. But if you get, programming well and programming in a way that can be reused and used by everyone is a whole field of its own. It's software engineering. And so the list of things you can look into to do better is pretty much never ending. We've linked a couple things we think are particularly helpful. Zach provided this link to the Chodra Lab, which provides software engineering tips for academics. So things like if you're familiar with these, continuous integration is one of them. I think there was some software design practices were in there as well. I've linked one of my favorite articles called The Mythical Man Month, which gets into the theory of programming and how to allocate people to get a programming task done. And finally, I also linked the solid principles, which are a series of patterns you could use in your code to make it actually more reusable. So if somebody understood your code, first of all, they would also be able to reuse it if you followed the solid principle. All right, so with that, I think I'm going to pass it off to Zach, who's going to talk to you about Colab.
Sorry about that. I was having trouble hitting the unmute button with 2 people controlling the mouse. Okay, let me look real quick. Before I start, can someone confirm that the link to the drive folder is in the chat?
Yeah, it is.
Okay. And while I'm going through the Colab tutorial, feel free to interrupt me if people have questions or need me to slow down or anything. Okay, so improving your code for non-coders kind of has different common practices than improving it for coders, because it doesn't matter if your code is readable if someone doesn't know Python or R or C or whatever you're writing in. So you're going to need the barrier to entry to be a lot lower. So you want things like easy inputs and outputs, like having an upload file button or a download button. And we want to do something like run it through a website, because they're not going to be able to easily download or install software. And the dependencies, for instance, if you have a conflict between 2 different versions of libraries, they're going to have a much harder time solving those, right? And it's likely that they're not going to be able to troubleshoot issues if you don't have like basic literacy in a language. And this is very important if you're doing something like a project in biology or something where, an experimentalist in biology might not need to know Python, but they might still benefit from an analytical method, right? some post-processing for their data or something like that. Okay, so these two are examples of accessible code. Here you can see on the right, this is from AlphaFold, where you just input into their user interface, you just input a protein sequence, and it will predict what the fold is for you. You don't need to look at the code, you don't need to see anything, but you can still run that. There's also this from Distill, or on Distill, where we have this nice little interface here where we can look at this, we can look at how these automata grow here, and I don't need to see any of the code at all. I can just move these and kind of very easily see what's going on. Okay. So one of the best ways to deal with this is through Google Colab. So it's a free service that allows you and other users to interact with a Jupyter notebook. And the servers even allow GPUs. So if you want to train a neural network and not use up some allocation on a supercomputer or something like that, or if you just want a user to be able to access your neural network on a GPU, it's very convenient. And it comes pre-installed with packages like Numpy and PyTorch, so it's really easy to get off the ground. And because you don't need to install anything, it's very nice for non-coders to use it, like that AlphaFold example I just showed. Looks like it's lagging a little bit. Oh, there we go. Okay. So Google Colab has a feature called Forms, which is what I was showing with AlphaFold, where you can hide your code in a notebook and add interactive elements instead. And it makes it very easy to interact with your code without actually knowing anything about it. So here I have the demo. It should be called Graph Forms in the folder if you're looking at that. Okay, so in this demo, I have a CSV file that just has 10 columns of data, and we're going to look at which one of these variables are correlated, and we're going to visualize it as a graph just for our example. But before we get into actually an example of using these, I'm just going to show you how to set up a form. So when you make a new cell in Colab, over here on the right, you have these three dots, and you can hit add a form. And you see now it's split into a left side with code and a right side with what a user would see. So anything, I can either edit, oops, sorry about that. I can either edit this text here, like I can just change to default title, and you see the comment changes on this side. Alternatively, I can edit it on the left side and it'll change on the right side, so they're synced. But that's not the useful part, just having a title. The useful part is that you can add fields here. So for instance, if I want the user to input some kind of string, then I can add this form here where it's just a text box. So you can see how it says variable name equals blank here. It's going to set whatever this blank is to whatever I type. So if I type in hello world, you can see that hello world automatically populates in the left side here. And there are all kinds of little interactable widgets like this that you can have where the user can enter in variables for your code to run off of. And you can see they're using this special character @ here. So if I delete the @ it deletes the form. That's how it knows that I'm trying to talk about a form in the actual code. Also important to note is that you can either hide the code or hide the form. You know, when you're developing, it might be annoying to have the form showing the whole time. And when the user is using it in the end, they don't need to see the code. Okay, so I'm going to delete this form and actually go through. So first I'm just going to import some packages. You can see that there's a lot of code here for like actual definitions of things, but the user doesn't actually need to see any of this. Here in this one, I have something important where I have Colab has a function you can import called, or like a class called files, where you can upload and download files So when I run this cell, that files.upload is going to make this button here where I can just access my files in the normal way you'd be used to in like a web UI. So I'm going to upload the CSV. It's just the example data here. And a good example of how this could be used is, if you want to post-process experimental data, this could be a CSV formatted in some way of someone's data from an experiment. Okay. And then let's say, we want to visualize the data, kind of think about which ones of these variables are correlated. So I have a form here where these are two drop-down boxes. In the code, they look like this, where I just have a list of options. Or you could, populate those with the GUI over here. Okay, so I drop these down and then I can pick some variables. And then when I run, it will visualize these for me. You can see, these two don't look very correlated because we can't really draw a good regression line through them. All right, this last cell, I'm showing a different feature of forms. You can edit the attributes and you can check whether to auto execute when fields change. So this means when I click one of these checkboxes or I use the scroller back here, it's just going to automatically update the graph. You can also change things like form width in the title here too. Okay, so I can type example title. I haven't run it yet. Sorry, so it's not showing. Yeah, so I can write example title, or I can, if I just delete this, then it'll just rerun it with example. Oh, it reran it while I was typing. And then I have a parameter here to show, I'm drawing edges here when things look correlated. And I have a parameter here to say, where's the cutoff for how correlated they are? So if I want it to only be the very most correlated things, I can scroll this over here. And if I want to show almost everything that's a little bit correlated, we can move it over here. And then I have some buttons to show things like, let's see comparatively how correlated these variables are to each other. And then we can get something like this visualization. So this would, something like this would allow someone to really access and play with code without having to know anything about it. And then this is just kind of how these things work here. So you can see the slider is just like a min max and a step. And then these check buttons are just Boolean arguments. Okay. So that's what forms look like. And that's how to use those. And I'm going to hand it over to Suhas to explain widgets, which are another type of interactive element that doesn't necessarily require you to be using Colab.
All right, hi. Hope this works, okay. Yeah, thank you, Zach. I'm going to be talking to you about Python widgets, which are similar to the interactive elements on Colab, but these are more generic to any coding platform. It's not restricted to Colab. And they're also portable in the sense that they can be embedded into HTML files on websites. So there's a little broader usability here. Let me show you a few examples on how they can be used. So here's an example that Levi generated for us. So this is going to be an image manipulation widget package, let's say. Let me show you how it works. Okay, so as per usual, we have a block that imports all the packages needed. We can import those. And there's going to be now a function that changes the brightness of an image. So here there's an image of a raccoon that's been chosen. Here's a regular function, and you could interface with this function just by running it with different values, or you could create this interactive slider object. Now this slider object calls the brightness function. You can just change some value on the slider. That's going to automatically update those changes in the image. Here's another way to interface with it. So this is going to be a function to invert the colors on the image. Again, we have another interactive element. This time it's not a slider, it's actually a checkbox. So this is the normal image unaltered. And if we check X, it's going to apply this very dramatic change to the image. So finally, let's try to put a bunch of utilities together into this meme generator function. Very simple. This now has 3 different interactive points here. So we can change, so currently it's a cute raccoon. Let's make it terrifying. Invert there. Stuff of nightmares. And very easy to do without actually knowing how the code works. So I might as well just hide it. Just go into view, hide the code. Doesn't even matter. This is all we need. So let me show you one more example that really demonstrates that these methods are flexible and can be applied to virtually any problem. So here's a little more, a much less fun problem. So what we have here is a system of ordinary differential equations. These are used a lot in predator-prey dynamics, but that's the wrong spelling of prey, it should be E. But let's say we have some rabbits called X, and some foxes called Y. These equations describe how their populations change with time. And each equation depends on the birth rate of rabbits, or the death rate of rabbits, or the birth rate of foxes, which depends on how many rabbits they eat, and the death rate of rabbits. So this is really a system of equations, and it can get very involved to solve these systems for different initial conditions or parameters. So let me run some packages that we need for this. Yeah. While that runs, you can see I have this very long piece of code. It's about 100-ish lines overall. So it can be quite an intimidating task to go in and change little things. But I've run them through this widget. There are a few things here that I've implemented. First of all, we have this progress bar that will update how much of the code has run in a certain amount of time. So let me show you how that works. I'm just going to change the time span of this ODE simulation. So I've reduced it to 10 days. You can see it showed me how far along the code was at solving the system, showed me how long it took. It was about a second, and also how many iterations it performed per second. So this is actually a very easy to implement code block. All I did was I wrapped ODE solver function with this TQDM method. Now, TQDM is a package that creates these progress bars in the terminal output. It's just this line and then another line within the function that updates, and that's it. There are many ways to do this. If you go into the documentation for TQDM, I can give you very useful information on how well your code is running. Now let's see how these populations change when we alter, maybe, let's say, the number of foxes we have initially. Right now, we're seeing rabbits in blue and foxes in orange. Now, if we change the initial number of foxes from 1 to 5, we're going to see something very different. Yeah. can see they quickly die out. But this is just a simulation, so they're able to pop back up from a population of 0. This is a phase representation of the same thing. Now, this kind of widget can be very useful when trying to create resources for people who really don't need to know how the code works at all. For example, you could be teaching it or doing some kind of outreach with completely lay people who don't need to know this, but perhaps this would be useful. And we can certainly see the utility of this when trying to educate or communicate science in times of pandemics and things like that. With that, I'm going to pass it on to Levi, who will talk to us about how to use these kinds of things in R.
Actually, I'll be showing you how to use him in R. But Google Colab is a handy tool because it not only works with Python, but it can actually work with several different programming languages. And today I'm going to be talking to you a little bit about using R with Colab. And you can do that by clicking this link or typing this to your browser, and it creates a Colab notebook in an R environment. So you can directly start coding in R without having to worry about Python or anything else. And then here, I'll show you an example of using Collab Forms with R as well. And it works pretty much in the same way as you do in Python, where you can create like drop-down menus or areas to type in text, where it assigns that to variables, and you can use that variable in your code. However, one thing that I found when using forms for R is that some aspects may not work. Specifically, the Boolean function where you can create checkboxes does not work because the syntax for Python is not exactly the same as for R. But overall, you can make easy to use forms where you can like adjust different parameters and create plots or any other outputs very easily. Click on this. And so the data that I have here is just from a tutorial that I found online, which they have population data from Midwest counties in the US. And I'm just creating a simple dot plot of this data. And you don't have to see any of the code at all. You just run it and you can see the plot here. And you can change different parameters, just like the thickness of the line, the labels, what you're plotting on the X and Y axes. And then it will just update your plots. And here's additional examples where you can segregate it by different states and plot it again. And what I find, I think, useful about forms is that it's an easy way for you to get like readers of your papers to interact with your data and your results. So you can think of it, you can link the form to download your publicly available data set directly and have them run the same analyses that you ran when you created your results, or even have them be able to tweak different parameters and see how that can alter the results as well. So it's an easy way for you to let people interact with your data and your analyses without having them needing to know R at all. So in conclusion, hopefully we gave you some ideas on how to make your code more accessible. We provided some ways to make your code more accessible to coders using some of these options that Levi presented. And we offered up Google Colab Forms as a way to alter your code for non-coders using Python and R, as well as using widgets that can be used independently of Colab. So I think now we'll take any questions if you have any. If you want any more details on any of the demos, we can provide that as well.